Good morning. This is Dr. D.K. Sharma, professor in pharmacy. So today we are going to discuss about the pre-formulation. So let's try to understand what exactly the pre-formulation is. This pre-formulation word comprises of two words. Number one is the pre and second one is the formulation. Pre means before formulation of any dosage form, whatever we do, that is known as the pre-formulation. So there are the certain parameters which will specify how we have to proceed for the pre-formulation. So one by one we will discuss these parameters. As the name indicates that physicochemical properties of the drugs are of the prime importance as far as the pre-formulation is concerned. And one such physicochemical property is the solubility. So first we will try to understand what the solubility exactly is. Solubility. Solubility means whatever amount, or say for example how much amount of the solute is available in a particular solvent, that is known as the solubility. Now the question arises, why this solubility is so important? The reason is that unless and until the drug will not be available into the solution form, it may not be available in the ionized or unionized form. And you know that pKa is again very important. What is the pKa? pKa is that amount or that percentage of the drug which is unionized in a particular solution. That is why we are going to discuss about the pKa also when we are discussing the solubility. So now what this pKa means? The unionized amount of the drug, because the nature of the unionized amount of the drug is the hydrophilic or lipophilic. We need to understand this particular part. So this is lipophilic in nature. And another important thing, that our biological membrane is also lipophilic in nature. So like dissolves like factor will imply here, and that is very important. We need to understand that particular part also. So whenever your pKa is say lipophilic in nature of that particular drug, so it can easily cross the biological membrane. So another part we need to understand here is that whenever a drug will be soluble into the water, it will be available either into the unionized form or ionized form. So what is our requirement? Our requirement is that it has to be available in the unionized form. That is why I am saying that it has first go into the solution. Now the question arises that why we are emphasizing on this particular solubility, that the drugs have to be soluble into the water. The reason is that nowadays the most of the scientists, they are developing new drugs based on the combinatorial chemistry. Now what is this combinatorial chemistry? You may ask me one question also. Combinatorial chemistry means having the changes on the various functional groups. We are mainly concentrating on the therapeutic efficacy of the drug. You might have heard about that. CAD, computer aided drug designing. Have you ever heard about that? Yes, you may have. So what they do usually, they will change simply the functional group and they are concentrating mainly on the therapeutic efficacy. So they do not have much emphasis on the solubility. So it becomes our duty to make the drug soluble. So now the question arises, how we can make the drug soluble? There are so many parameters by which solubility can be increased. The number one parameter is the solubilization. Micelle formation, you might have heard about that micelle formation. So we will take the surfactant and these surfactants will form the micelles. There are the certain other parameters also, like temperature also. If you will increase the temperature, the solubility also has been reported to be increased. But again, the reason is that, well, always with the increase in the temperature solubility will always increase. Answer is no, because there is a limit. Up to certain limit, this will increase the solubility. Now say for example there is a increase into the 10 degree of the temperature, there may be increase, the solubility may be double also. It may be possible that when you will go for increase in the temperature for next 10 degree, then the solubility may be decreased also. So up to certain level or up to certain range, the increase in the solubility will be observed. So this is the basic limitation of the temperature. Now question arises that what are the other parameters by which solubility we can increase? Yes, there are the other parameters also. Number one was the temperature, and second one is the you might have heard about the complexation word also. So complexation means you will take some complexing agents. What are these complexing agents? These complexing agents are the substances which will have the very less toxic effects, or rather negligible toxic effects. When these are combined with your drugs, these will have the complexation with your drugs. Since the solubility of these complexing agents may be very high, and because of that the overall solubility will be increased. For example, you can take another example of the cyclodextrin. See, the structure of the cyclodextrin is like this. Now what will happen? The drug will be entrapped into the cyclodextrin. So as a result, cyclodextrin itself is having the very high solubility. So what will happen? Once the cyclodextrin will go into the water, it will carry the drug into the water also. As a result, the solubility will be increased also. Now there are the certain other techniques also. You might have also heard about one technique that is known as the hydrotrophy. Now what are these hydrotrophy? Hydrotrophy is a process in which the role of the hydrotropes is again very important. Now again the question arises that what these hydrotropes are. These hydrotropes are the such substances which will have the very high solubility into the water. Why I am using this word very high solubility? Means these are extremely soluble into the water. One such example is the urea. We all know. But the problem with the urea is that if you will consume the large amount of the urea, these can sometimes be very harmful also. Now, we will discuss about the harmful effects of the urea later on, but first let's try to understand how this can increase the solubility. Now, when this urea, say, or other hydrotrophic agents, these are mixed with the drug, these will have the ability to increase the solubility. How this will increase? Let's try to understand. Say you will take one part of the drug, one part of the hydrotroph, and again you will go on increasing the amount of the hydrotropes. For example, one part of the drug, one part of the hydrotroph, one part of the drug, two part of the hydrotroph, and so on. Three parts of the hydrotroph, four parts of the hydrotroph, and six parts of the hydrotroph, seven parts of the hydrotroph. This is how you will go on increasing the ratio of the hydrotropes. And you have to find out at what ratio the highest solubility is being observed by using the various analytical tools. And this is also not important that when you will go on increasing the concentration of the hydrotropes, always there will be increase into the solubility. No, this cannot happen. This may be possible that up to certain limit solubility will be increased, and thereafter the solubility can be decreased also. So that is why it becomes at most important to find out that particular ratio at what the solubility is highest. So this process is known as the hydrotrophy, and the agents which are used to increase the solubility are known as the hydrotropes. Now we will take the first question where I discuss that, say for example urea is hydrotroph, it is having the toxicity. Yes, because higher amount of anything in the body act as a toxic substance. So if you will consume the large amount of the urea, this may cause the toxic effects. So how we can rectify this problem? This problem can be rectified by using the multiple type of the hydrotropes. You will ask that what this multiple type of the hydrotropes are. Yes, I will explain about that also. Now in this particular process, what we do, instead of taking only one hydrotroph, we will select 2, 3, 4 or 5 hydrotropes. So as a result, what will happen? The solubility of drug into hydrotroph 1, solubility of the drug in hydrotroph 2, and subsequently in 3, 4 or 5. If these are collectively mixed, ultimately the solubility will be increased also. This is the basic fundament, and this is known as the mixed hydrotropy. This is how we can serve our purpose of increasing the solubility also, and on the same time we are also reducing the toxicity also. So this point of reducing the toxicity is also resolved. So this was the one technique that is known as the hydrotrophy solubilization. Now you might have also heard about the other technique which has been very widely used for increase of the solubility also, that is known as the co-solvency. This method also applies that, for example, the drug is having the solubility in solvent 1, some solubility it will have. In solvent 2, it will have again the different kind of the solubility. In solvent 3, it will again have the different kind of the solubility. In solvent 4, it may have again different kind of the solubility. If you will mix collectively all the solvents, what will happen? The overall solubility of the drug will be increased. So this particular process is known as the co-solvency. And because of the co-solvency effect, the ultimate solubility can also be sometimes increased also. There is one last technique also. So there are the various other techniques also, but actually since we are discussing about the pre-formulation, so we have to restrict our lecture to certain points. One last technique is that is known as the solid dispersion technique. In the solid dispersion technique, instead of using the hydrotropes, we use various types of the polymers, and these polymers again should have the solubility into the water. Now, how these solid dispersions are useful for increasing the solubility, let's try to understand. In this particular process also, what we do, we will take one part of the drug, one part of the salt dispersion part, I mean polymer we will take, and this is how we will go on increasing the ratio of the solid dispersion part, or rather you can say the amount of the polymer we will increase. For example, one part of the drug, one part of the polymer, one part of the drug, two part of the polymer, one part of the drug, three part of the polymer. This is how you will go on increasing the amount of the polymer in ratio, in a well defined ratio. 1 ratio 1, 1 ratio 2, 1 ratio 3, 1 ratio 4, 1 ratio 5, 1 ratio 6, and this is how so on you will go on increasing. And again we have to try to find out at what particular ratio the maximum solubility of the drug is being observed by analyzing the drug by various techniques. So this particular technique is known as the solid dispersion technique. Now the question arises, what happens in this particular case that solubility will be increased? So in this particular case, what we do that when drug and the polymer is being added in presence of some solvent, so what will happen? The solvent, because of the presence of the solvent, there will be some sort of the interaction between the drug and polymer will occur. And you also know that drugs are either present into the crystalline form or these are available into the amorphous form. Now, here also we have to discuss somewhere that crystallinity and polymorphism, but later stages we will discuss, but I will give you some idea about the crystallinity and amorphism of the drug also. Now, amorphous drugs are having the higher solubility in comparison to the crystalline drugs. Why it is so? Because in case of the amorphous forms, there is not the specific structure of the drug particles. While in case of the crystallinity, crystalline drugs, there is a specific structure of the drug. As you can see here, in case of the crystalline drugs, there is a definite shape and all the molecules or drug particles are attached to each other with a specific shape, and a bonding is also available there. So breaking these molecules in presence of the water will be difficult. That is why these crystalline molecules are having the lesser solubility in comparison to the amorphous. While in case of the amorphous, what will happen? The drug particles are not bind to each other with some specific shape. The moment you will add the amount of the water, the hydration energy is sufficient to break those particular particles and it will get dissolved into the water itself. This is the basic difference. Now, the question arises that how this will crystallinity and amorphism will help in increasing in the solubility. Let's try to understand. Now suppose there is a crystalline drug, because this is the mainly point of concern for us, because amorphous drug is having the already good solubility, so we don't make any changes into the amorphous drug. We have to make the changes, or we are mainly concerned about the increase of the solubility in case of the crystalline drug only. Now when this crystalline drug in presence of the polymer will interact in presence of the solvent, so what will happen? This crystalline drug either may be changed into the amorphous drug, or it may also be changed into the different polymorph also, or you can say in different crystalline form also, and that crystalline form may be more soluble in compared to the previous one. So this is the basic mechanism of solubility enhancement in case of the solid dispersions. So that is how the solubility is basically expected to be increased in case of the solid dispersion technique. This is the basic process. Now there are the certain other facts related to the crystalline and amorphous drugs. See, in case of the crystalline drugs or crystalline forms, it will have the internal structure, as I have already told you that it will have the internal structure. A specific structure is there. That is why it will have the good binding of the molecules among themselves. Whereas amorphous drugs, these will not have the fixed internal structure. That is the major problem with this. There are the certain other points related to the crystalline form. It is more stable. It will maintain its structural stability or integrity for a longer period. It will remain in the form it is for a longer period. The reason is that again the molecules are bound to each other with, say for example, wonderful forces may be of the good strength, or sometimes the covalent bonds may also be present. That is why it is more stable. It is more stable than its amorphous form also, while it is not stable. So what will happen in case of the amorphous drug? When you will put the amorphous drug in presence of the environment, it will have the ability to convert into the crystalline form, more stable form. That is the basic problem with the amorphous drugs. So that is why we can say it is less stable in comparison to the crystalline forms also. Again, important thing we have discussed, since amorphous forms are the less stable, so these will have the better solubility in comparison to the crystalline drug. Why? Because their particles or their drug molecules are not bound with the some high strength forces, while in case of the crystalline drugs, what we have studied, that the drug molecules are bound to each other with the high force of bonds. That is why it will have the good solubility, while in case of the crystalline forms the solubility is less. That is why we need to convert the crystalline drugs into the amorphous form when we talk about the solid dispersions. So this was the another technique that is known as the solid dispersion technique for increase of the solubility enhancement. So these are the certain techniques which are basically used to increase the solubility. Now we will talk about the bulk characterization also. How this bulk characterization will help in deciding the pre-formulation studies. As already I have told you that in case of the bulk characterization, there are the two different parts of the crystallinity and polymorphism, that is the habit and internal structure. In case of the internal structure, I have again tried to make you understand that crystalline and the amorphous drugs, what kind of the structure they will have. Already I have told you, in case of the amorphous, that no structure is available, while in case of the crystalline, a specific structure will be available, and the various structures which are available in case of the crystalline drugs are like platy. We can have the massive needle type of the structure also we can have. The best example is the aspirin. when you will put the aspirin into the various solvents, you can have this kind of the structure also. Sometimes you can have the bleeded structure also, sometimes you can have the tabular structure also, sometimes you can have the prismatic structures also. So these are the various types of the structures of the crystalline drug also. One more important point about the bulk characterization, I would like to tell you that despite of having the crystalline and amorphous forms, we have the polymorphs also. Polymorphs means a crystalline drug can be available in more than uh, one type of the habit, that is known as the polymorphs. Like drug can have the polymorph A, polymorph B, polymorph B. Now the question is why we need to understand or why we need to identify these kind of the polymers. Let's take an example. There is a drug that is known as the getafloxacin. It is antibiotic. Yes, it is antibiotic. And Ranbaxy was preparing this drug. And during, while making the tablets, what happened? A crystalline form was converted into the different types of the form. And ultimately, what happened? The kind of the therapeutic efficacy was expected initially, it was not providing that kind of the efficacy. The scientists were also very worried about that particular thing, why it is happening. They were not able to identify the problem. Then they realized that during the punching, what happens? Approximately 80 degree of the temperature is being imposed on the die and punches. That is why what happens? This high temperature was mainly responsible to convert a polymorph A into the polymorph B, and polymorph B, which was generated of the getafloxacin, was having the lesser therapeutic efficacy. So this was the major problem associated with the polymorph. So you can imagine that how important these polymorphs are, right? So next parameter which we need to understand is the hygroscopy. Hygroscopy means whether the presence of the water or moisture is available there into the drug particles or not. Now you can ask how this can affect the drugs. See, there are the certain drugs which may be sensitive to the presence of the water. One such example is the salicylic. You might have heard about the aspirin. What is the aspirin? Aspirin is formed from the salicylic acid. Do you know it? Yes, you might be knowing it. This is the acetyl salicylic acid. When you will put even small amount of the water, or presence of the water is there in the atmosphere also, so that water can be absorbed by the aspirin immediately and it will be hydrolyzed. That is why we need to understand whether the drugs are having the moisture consuming ability or not, or how much moisture is available in the drug, that also we need to identify. Now the question arises that how we can identify the drug. There is a range, yes. Hygrometers are all available into the market, so with the help of that we can identify how much drug is available, right? So this was the second part. Next part is the fine particle characterization. Now, what is the importance of the fine particle characterization? Let's try to understand this part also. Now, particle size also is very important as far as the pre-formulation studies is concerned. The particle size can be determined with the help of the microscopy. There are some other tools also, we will discuss about those also. Now the question is what should be the specific particle size or what should be the ideal particle size. Now if the particles will be large, then what may be the problem? There may be the problem of the absorption also. There may be the problem of the, in case of the formulation also. So therefore we need to reduce the particle size up to certain limit. Now the question arises that how much particle size we can reduce. Should there be any limit? Obviously the answer is yes. It has to be reduced up to certain limits. Say for example, if you will decrease or you can reduce the particle size, ultimately what will happen? The overall surface area of the drug particles will be increased. Okay, the overall surface area of the drug particles will be increased. So as a result, what will happen? The absorption will also be increased. When the absorption will be increased, there will be the better chances of the therapeutic efficacy. Now again the question rises, previously also I have told you that up to what extent you can reduce the particle size. Can you reduce below the 10 microns, 5 microns, 2 microns? No idea? Okay. If you will go on decreasing the particle size, what will happen? Electrostatic charges may be generated. As a result, what will happen? The smaller is the particle size, more will be the electrostatic charges. So they will try to come closer to each other. And as a result, agglomeration will start. Okay. Now this agglomeration will result into accumulation, and again the larger particle size will be generated. This may sometimes also result into the bad pre-formulation of the drugs, or your dosage forms may be destroyed also. Your dosage forms may not provide the therapeutic efficacy we were expecting in initially. So this is why that the particle size has to be reduced up to certain level, but not below 10 micron. So this thing actually we have to take into the consideration. So there are the certain techniques which can be used to reduce the particle size. There are the various methods you might have studied during the unit operations. So these were the certain parameters which will help you out to provide the pre-formulation studies, and this is how you can get the better dosage forms. So today we try to had a better idea on the solubility, bulk characterization also. So these were the some of the important points. Though there are the certain other points also. In next class we will try to understand this part. But in this particular part, to conclude or to have an overview, I would again tell you that the pre-formulation is basically a technique where whatever we do for making any dosage form is known as the pre-formulation, or whatever studies are done before making the dosage form, that is known as the pre-formulation. And we will study the various parameters. The one of the such physicochemical parameter was the solubility. As already we have a discussion about the solubility also, what are the various types of the solubility, how we can increase the solubility, and what will be the role of the crystallinity, polymorphism, amorphism on the solubility enhancement. So I hope that you might have understood about the insight of the various parameters in case of the this pre-formulation. And if there are any doubts, we will have a discussion on that also. With this, I come to end of this lecture, and thank you so much for patiently listening my lecture. Thank you. Thanks a lot.